Hello, so welcome to Intelligence Healthcare and its Applications course. And so we will continue on the part two of our today's agenda, which is the neural network and its applications. So in the part one, we have introduced the simple neural network, which contains only one hidden layers of neurons. And we also introduce what is the perceptron and how these mathematical neurons can mimic the behaviors of the real neurons in our brain. So you also see that we apply this simple neural network to the PSQI data we have shown in the previous logistic regression course. So you also see that this simple neural network can perform very well in this data. So let's continue on this journey. Okay, so let's first take a look at what's the difference between simple and deep neural network. So as we have talked in the previous course, that the major difference between simple and deep neural network is the number of layers. So in a simple neural network, there's only one hidden layers. However, if you just add more than one layers in the neural network, then it will significantly increase the number of connections between each neurons, and also the computation time and the amount of the computations. Okay, so in the deep learning neural network, the information of the input will pass through multi-layers of neurons and finally converge to the output layers, which contains several classes of classifications. So one of the advantage of the deep learning neural network is that we expect this network can process more complex informations. However, this also comes with a limitation that it is very difficult for a usual computer to compute this large amount of the connection informations. So it takes actually about several decades for mathematicians and computer scientists to figure out how to find an algorithm to efficiently calculate the weight and the connections between each neurons. So in terms of the development of neural network, it is closely related to the study of the brain, and especially the study of the visual functions or the visual information processor in our brain, so-called the visual cortex. So in around the 1950s, there were two scientists, Hubble and Wiesel. They did an elegant experiment to find out the visual cortex in the brain. At that time, they were able to record electrical signals in the brain, and they were also able to design an experiment to fix the cat in an apparatus and to give the visual stimulus and see which part of the brain can respond to the stimulus. So in one of the interview of the Hubble and Wiesel, they admit that they were actually very lucky because they actually tried several areas and tried to find out which stimulus can generate electrical signals in the brain, and they find out that actually this is one of the primary visual cortex in the occipital region can do this kind of job. So based on their study, now we know that in this primary visual cortex, the neurons actually are arranged in a very regular manner, in a very columnar manners. So these arrangement of the neurons is actually correspond to the visual stimulus on the retina. So we with this the neural network arrangement, they found that these visual images can be processed within this region, and it's just like a filter. So it can send out the filtered information to the other part of the brain for further processing. So this is amazing studies that also inspire the computer scientists and mathematicians to develop a neural network that can be capable of seeing something that we is similar to what we have the mechanism in our brain. So let's get back to our challenge. Is that so? If we want to develop a neural network or algorithm to visualize, to see an image and to see what we see. So the first thing we need to do is that how to digitize an image. So for any computer imaging data, it is actually a combination of the binary informations. For examples, when you see the pictures here, then if you are able to just magnify this region on your screen, you should be able to see a tiny pixels just like this one. So in computers, we always use discrete informations to simulate an analog information. So for example, the line here are analog because there should be no boundaries, or there's no very rigorous distinctions between each point of this line. However, if you are able to cut these figures or images into several squares, small squares, then we should be able to determine that in a certain location of the pixels, we should plot a black square here. In other part, it should be remain in a white. So using these ways, then we can digitize this image into the binary images, which is shown in the right. So we can just designate the white as 0 and the black as 1. Then you're able to see the image here. And you see that probably here is not, there should be a 1 here and not a 1 here. So it's still a little bit different from this one, but just want to let you know that is the way how we digitize an image. Okay, so for a black and white images, then we can just use the 0 and 1. And if there's a gray images, then we can divide the gray colors according to spectrum between 0 and a certain range of the number. For example, the 255. So here you can see that using a two-dimensional matrix, then we can assign a number to each pixel, and that number is corresponding to a color scale. So in the case of the gray images, for example, if we just divide the range between the totally white and totally black into like 256 scales, which is the power of the 8 to 2, then we should be able to use the number from 0 to 255 to correspond this number to a certain level of the gray color. So this is the case of the black and white or gray matter images. And in the colored images, it is also, we can also do this in a similar way. The difference is that each color can be decomposed into 3 original colors, which is the red, green, and blue. So use the combination of the red, green, and blue colors, then we can generate virtually any colors just by 3 numbers in our images. So in the case of the black and white image, there's only 2-dimensional array, but in the colored image, because there were 3 original, you can decompose the original color images into 3 colored images, which is green, red, and blue. So it's virtually the 3-dimensional array, not just only 2-dimensional. So that is how we digitize color images into 3 different layers. Okay, so the purpose of the neural network is just like this one. So we need to develop an algorithm that to input images into our neural network, and the output should be one of the several classes. For example, in the algorithm need to identify the happy face and also the sad face. So the one of the pioneer in the machine visual ability is the ImageNet developed by the Stanford University. So if you look up the ImageNet on the internet, you should be able to find out this website. And it has a large collections of the images. So far, they have more than 14 millions of images in this database. And they have classified these images into more than 21,000 classes. So many people or many research teams have used these resources to test their algorithms. Actually, the Stanford also provide a unique challenge each year since 2010, and to try to find out the new applications of the neural network in terms of the image classifications. Okay, so if you are interested in these image challenges, you can look into the ImageNet. There are several, not only they have a large collection of the images, they have also very rich of the resources to tell you how to do the neural network in these databases. So one of the major development based on ImageNet is since the 2010, when the first one of the first neural network was developed at that time, which is convolutional neural network. And you can see some of the examples from the ImageNet. So, for example, if you develop an algorithm that that algorithm to see what is in these pictures. So there's a cheetah in these pictures, and the algorithm is correctly identified this is cheetah. But also, you will generate the probability for the other animals, but the probability for the cheetah is much higher than the other one. So we can say that, okay, this algorithm can correctly identify the cheetah, but not leopard or snow leopard or Egyptian cat. And also this one, the algorithm can also identify this is a bullet train and not passenger car or subway train or electric locomotive. But to do this, we really need lots of the human work to label each images as one of the non-classes. So for example, we need to tell machine that this is cheetah, and probably not, the only one image is not enough. We actually need more hundreds, thousands of, even more than thousands of images, and to tell machine that these images are, for example, cheetah, leopard, and other animals. So the machine can learn from these non-labels and to train the neural network models. And at the same time, you can also see that there's are some limitations about the convolutional neural network. For example, if you have these special images, this looks like a hand glass. So, but because of the color of this handle, the algorithm will think that, okay, this may be the scissors, okay, and the correct answers has a lower probability than these incorrect answers. So that sometimes it's just not very easy to identify what's the object it is. So you can see that the other probability about the frying pan and stethoscope is also high. So that is the challenges we need to solve in the field of machine learning. So you can imagine that if you are using just a simple neural network, it is very difficult to achieve this kind of the complex job. So because for an imaging data, there are lots of the input values, and just not only few of them. So in previous course, we showed that this simple neural network can do very well in the PSQI data, which contains only no more than 20 variables. So in the case of the images, there are usually not just hundreds, but thousands, more than 10,000, even millions of the pixel data. Then it is almost impossible for those large amount of data pass through these neurons and to derive correct answers. So we really need a new method, and that method comes in 1989, which is developed by the young LeCun. And LeCun is a very talented computer scientist, and he developed new models of neural networks, which is called LeNet at that time. And if you examine this neural network, you will find that actually the later parts of this network is consistent with the deep neural network. It contains the two hidden layers, which is C5 and F6. Okay, so in the C5, there are 120 neurons. And in the F6 layer, there are 84 neurons, and they are all fully connection layers. And before this deep neural network, the LeCun developed a very special technique or algorithms to process the images. And the idea is very simple. He thought that if we can derive the features of these images and to reduce the number of the information by extracting these features, then we should be able to reduce the number of inputs to a reasonable number of inputs into the deep neural network. So that will prevent lots of the problems from such as the overfitting or the huge amount of the input data. So in this case, the input size is about 32 by 32. So you can see that there are already more than 900 input pixels. So we really need a certain procedures to reduce the amount of the information, even there are only more than 900 pixels. So the way developed by LeCun is using a convolution and subsampling. So the convolution is really a innovative way and dramatically change the way we use the machine learning. So this is a very early prototype of the convolutional neural network. So this is one of the typical examples of convolutional neural network. So for each images, we will use convolution and pooling to reduce the dimensionality of the image into a reasonable number of the input. So from large images, we will use convolution to extract features and to find out the common features in this feature map, and finally just convert these two-dimensional images, the features, into a one-dimensional input, and the other part of this actually is a conventional deep neural network. Okay, so probably you are wondering that what is convolution. So the convolution is a mathematical term, but to illustrate this convolution intuitively, let's cite these figures from the superdatascience.com. And so in the left, you will see an example of the input images, which is only binary data, contains 0 and 1. So for convolution, we need a feature detectors. The feature detector defines a certain patterns. For example, here we can define the patterns which is 3 by 3 matrix, and there is only a value of 1 in this and this and this and this region. So you can see that, okay, it try to detect patterns, maybe just like kind of the angle patterns here. So if we apply these feature detectors to these input images, then we will compare any 3 by 3 squares data to these feature detectors to see if these 3 by 3 squares is a match of these detectors or not. So we can just simply multiply these 3 by 3 matrix with these feature detectors to derive a number here. So how do we do this? So you can just look at this pattern. So here is in the left upper corner is a 0, and this is also 0. In the right upper corner is a 0. In the feature detector, it is 1. So if you multiply by the corresponding values in the corresponding locations, you will sum up these values, and because there was no matching patterns here, so you will derive a number of 0 here. And if you just move these the windows one step into the right, then you can see that there's only one patterns matched in this 3 by 3 matrix, which is in the middle left, the pixels. So in this case, you can, because 1 multiplied by 1 is 1, but the other pixels are the results are 0. So the summation of all these 9 combinations is 1. So we can do this by sliding windows throughout the whole images. Then you can derive the numbers into the feature, we call the feature map. So you probably already noticed that using the feature detectors, although this feature is only 3 by 3 detectors, and the original input is the 7 by 7 input, But using these feature detectors, you can reduce the data into this only 5 by 5 matrix. But you probably will be curious that this feature map seems to be very distinctive with original input images. And that is true. But imagine that because we are using a certain patterns of the feature detectors, so the resulting feature map should be contains information that was extracted by these kind of patterns. And that is so we can use some example to visualize these mechanisms. So the convolution is actually a powerful mechanism to extract the image features. So for example, everyone has experience to process your photos. So for example, in your smartphone, you probably have experience to adjust the lightness or the contrast or even the color distribution of your photos. And that was done by lots of different kinds of the convolution layers. For example, here, if you define this kind of the feature detection map, and which defined by the center is multiplied by 5, and the surrounding 4 corners are defined by -1. So you can see that if you apply this feature detection patterns to these images, then you will try to enhance anything in the central pixels. So the resulting effect is to sharpen these images. So that is one of the very common filters or algorithms we used in our smartphone. And the other examples is probably the edge detection. So in that case, we can ignore the central pixels, but try to enhance the surrounding pixels. So using this feature detection map, then we can actually find the edge of these pictures. And it is sometimes it is very useful in the imaging processing software. So now you know about the convolution. The convolution is actually a feature detections. And so for an input images, we can use different kinds of the feature detection map to derive lots of the feature maps here. So the number of the feature map will determine the ability of your algorithm to identify the critical patterns to classify the images. So usually we will use more than one feature detection patterns to derive the feature maps. So for one input images, we will derive several convolutional layers or feature maps in the convolutional layers. And so we need some way to combine information from these feature maps. And that is we call the rectified linear unit. We call it ReLU layers. So the rectified linear unit is just like the right one. And remember in the previous course, we talked about threshold functions. And the function means that we need to process this information and to output a simple information that can characterize the complex information of the input. So for the rectifier, the horizontal axis is just like the summation of the information, and only it passes a certain threshold, it will have a linear response to the input values. And that is important because in these feature maps, it is not all informations are important. For example, let's go back to these slides. So here you can see that using these feature detectors, there's only information here are important because it represents that it has a totally match of the information of the feature detectors, and even the surrounding pixels are also important because it has also has a larger numbers, meaning that it has the pattern is close to these features. Okay, so let's go back to this rectified linear unit. So we need threshold functions to determine that which features are important or not. So we can further reduce the dimensionality of these feature maps. So what does ReLU do, which is called rectified linear unit? So with these images, and once we use the feature map or feature detectors to process these images, then we can use ReLU to simplify the informations. So here you see some buildings, okay? So, but within the buildings, you also see windows that is clearly has a black and white distinctions. So to visualize, visually we can easily identify those are windows, but to our brain, we also see the distinction between these white and the black and white lines. So the ReLU actually see the similar things. It should see the rough boundary of the buildings, but at the same time, they also see some windows here. And you probably see that, oh, this is not clear. This is just very rough images that is not, we don't understand what it is compared to this one. But because remember that our brain is very capable of interpreting information. So although, okay, we can easily tell what are things inside these images, but for the computers, they need to reduce the dimensionality of the data or information into this one, so they can process further in the neural network models. And I will show you that later. Actually, in our brain, we also do the very similar things. Okay. So let's go back to this the architecture of the convolutional neural network. So we already talked about the convolution and ReLU. So the combination of the convolution and ReLU, we can reduce the dimension into a smaller amount of the data. Then we need the pooling layer to integrate this information. And what does that mean? So for example, if you have a collection of the leopard images, then we need to ask ourselves that what is the common feature in these leopard images? You can see that some of leopards are lying down on the ground, and this one is just sitting on the ground, and this one we can only see is the head, and this one seems to be sneaking for his prey, and this one is comfortably lying on the ground, and this one just look at something. Okay, so they have a different postures and different the locations to be captured by our camera. So maybe the common features in these images is those black and brown color patterns. Okay, these black dot and brown color patterns defines the leopard, and so if we want to develop an algorithm to classify all these images as leopard, then we really need our algorithm to capture these important informations these black dots, but not the posture of these animals. Okay, so that is the purpose of the max pooling. Okay, so the max pooling will try to find out the common features in the feature map. So you can see that this, for this feature map, we will find out the maximum values of these regions, which is the 1. And you can do this one by one to find out, okay, so this one is 4 because it contains this largest number here. So we can further reduce the dimensionality of the feature map into a smaller dimension of the pooled feature map, which is the important features of the original images. So that is called the max pooling. So the convolution pooling is a procedure to extract the features in the images and to pool these features into a reasonable dimensionality of the data. Okay, so back to this architecture. So we can repeat the convolution ReLU and pooling layers for several times, and to reduce the dimensionality of our input image into a small number of the inputs, so that we can use this small number of the inputs to fit into our neural network. So that is the one of the greatest the invention in the machine learning fields, because once we have these feature detection mechanisms, and also we can efficiently reduce the dimensionality of the data, then we can use this information to do a very good classifications. Okay, so the final step is very simple. We just suppose that this is the pooled feature map we derived from the original images. Then we just flattening this two-dimensional matrix into the one-dimensional matrix. And you can see that we just sequentially put these numbers into the one-dimensional vectors. So for example, the first line is a 1, 1, 0, and we just put the second lines following the first line. Here is 4, 2, 1, and the third line is 0, 2, 1. So for the 3 by 3 two-dimensional matrix, we can convert or flatten this two-dimensional matrix into the one-dimensional vectors. So using these one-dimensional vectors, we can use this as input values to our neural network. So the flattening is actually the final steps of the convolutional pooling layers, and the rest of things is the same with the artificial neural network, which is we have introduced in the previous part of the course. So this is we can simply say that the convolutional neural network equals to feature detection plus artificial neural network. So the right side is the conventional deep neural network, but the left side is the feature detection process to find out information in our images. Okay. So let me show you one of the examples we have developed in our lab. So in the process of the MRI images, one of the critical step is to calibrate the brain positions. So why is that? Because imagine that you are lying, you just lie down on the bed in the MRI scanning room. Then each participants may have a little bit different shape in about their head, and also when you probably someone may just turn a little bit left to their head to the left, and the others may turn their head to the right, and so each one has a slightly different positions on the MRI scanning bed. So once we obtain these MRI images, we need to calibrate these head positions. So the way we do this is, for example, is the ACPC line. And the AC means the anterior commissure, which is one of the important anatomical structures in our brain. And there's also the posterior commissures here. So we need to align this ACPC line and to adjust the pitch of the brain. So the pitch is only one way to adjust the one dimensional of the head positions. There is also rho and yaw we need to carefully calibrate their position. For example, here this rho, we need to keep the brain in the central size, and the yaw, we also need to keep the brain in a symmetric way. Okay, so this head motion correction is very important step in our MRI pre-processing analysis, and oftentimes we need manually input these rho, yaw, and pitch values. And we already developed CNN algorithms to adjust, to find out the angles of these MRI images. For example, we can feed these original images into our CNN model. Then the model will tell us the angles we need to adjust in, for example, the pitch, rho, or yaw. And the purpose I want to show this is that although the model can give us these angle numbers, but what does really the model see in these images? So remember, in these CNN architectures, that the input images went through several times of the convolution and pooling process. But can we just visualize this feature map here? For example, in this case, then we just use the feature detectors to derive the feature map. So the purpose I want to show, can we visualize this feature map to see what models see in the CNN model? Okay, so let's go back to our slides here. That for this one, I just show you that, for example, if we use the 4 convolutional layers in our models, then we can visualize each layers to see that what is the feature maps derived from the original images. So you can see that this is the first convolutional layers, and the model definitely see the corpus callosum in our also brainstem in our MRI images. And for the second layers, it also see these prominent structures in our brain. But for the third and the fourth convolutional layers, it sees the same thing. It's not just it does not contain more informations. So that is why we decide to just use only 2 convolutional layers here. So you can see that even for the convolutional neural network, you really need to carefully determine that how many layers you want to use in your data, because not the more convolutional layers is definitely not the right answers for every challenges. You need to find the optimal layers of the convolutional layers in your data. So that is very challenging, because it's very difficult to find optimal layers. So there are some other solutions, but it's beyond the scope of this course. I just want you to know that we are able to see or to visualize what's the model see in these different convolutional layers. Okay, and this concept is actually very close to the visual research in the animal models. So for example, this is a paper published by Dr. Ye in the PNAS in 2009. And you can see that in these left upper corners, it is the visual stimulus given to a primate. Okay, so you can also see that the actual recordings of the visual cortex see that it has a certain processing of this information. The shape is very similar to what we see. And for the different layers of the neuron, you can see that it sees different informations. So it's very similar to what we have done in the convolutional neural network. And you can see that, and this is kind of feature detection map in our brain. Okay, so the convolutional neural network is actually inspired from these the visual research. Okay, so for today's course, I want to just show you one very important examples on the internet. And so I will use this example to show you how to do CNN in the MATLAB. And I will find time to give a more just full explanation of these models. But for now, I will just use these simple CNN models for the illustrative purpose. Okay, so you can follow this link to find out the documentation in the MATLAB to show you how to write just simple lines of the codes to process an elegant example data to recognize the handwritten digit. Okay, so for now, I will just go to the MATLAB to show you how to do this. Okay, so let's take a look at this the website and the web link. So this is a very elegant documentation to teach you how to do the CNN in MATLAB. So the first thing that we just try to load and explore the image data. The image data here is the handwritten images. I will show you this later. So you can just copy this comment into your MATLAB here. Okay. So so you can see that after this comment, so we can just load the image data into our variables, which is stored in the IMDS. So you can see that this IMDS variable is actually the image data store type of the variables. You can double click on this one. You can see that it contains the files, which is the 10,000 cells. And if you further click on this one, you can see that, okay, this is the file path of these images, which is, you can see that it is classified by the 0 and 1, 2, 3, 4 until 9. Okay, so because there are 10-digit handwritten images, but for each digit we have 1,000 images. So the total we have the 10,000 images here. So you can also see the label. The labels is corresponding to the files here. So each label is corresponding to the files, and this label means that the ground truth of the image data. So because these are the handwritten digit, so the ground truth is each digit from 0 to 9. Okay, And also there are other informations, but for now we just need to focus on the files, labels, and also read function here. So the read function here defines the way to read these data. And you can see that we are able to change these read functions. So this is a very useful features in MATLAB. So we can create different types of the image data stores. Okay, so let's just close this variable windows. Then let's go back to our MATLAB documentations. So the next step is try to display some of the images in a data store. And so these 6 lines of the code actually try to randomly pick up the digits in our data stores and to show up in our MATLAB. So the first line means that we just create a figure, a blank figures. And the second line is just try to find out the 20 random index in these 10,000 images. And this is, if you remember, we have done this in our previous course that we try to randomize the training and testing data using these functions. And for the next 4 lines, we just try to use the for loop. So we can just, from the first images to the 20th images, we can just plot them in a regular in a 4x5 image matrix. So the function to show these gray images is IronShow. So for the IronShow, we just try to designate the file names here. So because as we said that in the MATLAB, the data stores, the file path is stored in these files. So once we determine the number of the files here, then in the MATLAB, then we can just use this index to determine which image we will show in our MATLAB. So we can just copy these 6 lines and put into the MATLAB here. So let me close this window to you can easily show the results. Okay, so this is the results of so if you compare to these results should be the same. Okay, so you can see that each person has different styles in writing numbers. So that's why this is a very elegant database to develop an algorithm to identify the handwritten numbers. And so this is one of the typical neural network data sets. Okay. So let's close these ones and continue on this tutorial. So the next thing is that we need to know how many labels in this data. So, and this is very important because we need to determine how many classes we want to train in our models. So for this line, just try to tell us that how many labels in our data. So just paste into the MATLAB and see that there are 10 labels from 0 to 9. There are 10 labels, and for each label, we have equally 1,000 image in our database. So this is a very balanced data. Okay, and for the next one, we want to determine the size of the images. So the size size functions determine the size of the image here, which is 28 by 28. So it means that for each handwritten images, there are 28 pixels by 28 pixels size. Okay. Then the next one is very important. Remember that in the previous course, then we emphasized that for each machine learning models, we should divide the data into training and validation data sets, or training or testing data sets. So in this case, this documentation tutorial divide the data into training and validation so that each category in the training set contains 750 images, and the validation set contains the remaining images from each label. So we simply use the function provided by the MATLAB to divide the data into training and validations. And the function is called the split each label functions. So it will process the IMDS data store and to divide this into the training set and the validation set. So let's execute these two lines here. Okay. So you can see that in the right side, we already have two new variables, which the first one is the training data stores and the validation data stores. And if you double click this one, you can see that the original IMDS is 10,000 cells, but here we have only 7,500 cells. And in the validation, we have only 2,500 cells. Okay. So the next step is we can define the convolutional neural network. Okay. So in the MATLAB, it's quite easy and straightforward because you can design your CNN by change the parameters in these several lines of the code. So we can define layers as a collection of the different types of the layers. And for example, the first thing we need to do is we need to define the input layer. And because we already know that the input layer is the 28 by 28, but remember that this is only black and white gray images. So there's only one layer in the third dimensions. And if you are using the color images, then you should put the 3 here because you can decompose the color image into the green, red, and blue colors. So in this case, we can only specify the image input layers 28, 28 by 1. Okay? And the next is, remember that we need to do the convolutional two-dimensional layers. So here we can define the feature detection map by these parameters. And then we need to also do the normalizations and ReLU layers. And for once we have done the first step of the convolution and ReLU, then we need to do the max pooling layers to collect the feature data. And we can repeat these procedures for 2 times. So in total, we have 3 convolution and max pooling in our data. And the final step is the fully connected layers. So we can, once we have use our CNN convolution ReLU and max pooling to reduce our data into a certain number of a small amount of the input data, then we can feed this data into the fully connected layers, which contains 10 neurons. And the final is the soft max layer to give classifications. So please note that for this part of the code, it defines the feature detection, which is defined by the convolution, ReLU, and max pooling. But for these parts, it's actually the simple neural network. So there's no deep neural network in this model, but it's just combination of the convolution and the simple neural network. And of course, you can define the deep neural network here, and you can try to do it yourself to see if you can design truly see a deep CNN model. Okay, but for now, we can just copy these lines into our MATLAB here. Okay, so let's close this one to clearly see what is going on in the MATLAB. Okay, sorry. Okay, so let's paste these codes into the MATLAB. So nothing happened because we just defined the layers here, and you can see that there are 15 layers in our models. Okay, so if you double click on this one, then we'll show you, okay, the first is the image input layer, and then follows by the convolution 2D, batch normalization, ReLU, max pooling, again. So there are totally 15 layers. And the final layer, the softmax and classification output, is very important because remember that we use the softmax function to output the probability of each class. Okay, so if you have time, you should try to look at this the description for each layer, so you can learn more about the detail of these different kind of the layers in the deep neural network. So the next section is also very important because we need to specify the hyperparameters of our neural network models, and because our course, we do not intend to show the mathematical details of these hyperparameters. So I will suggest that just for now, you can just follow these options. Okay, and some of the critical parameter here is the initial learning rate, which defines the gradient descent of our to search the errors of our models. And also we can define the max epochs that we need to run the model. So the larger epochs will take more times to finish your training. Okay, so let's just copy these lines into the MATLAB, and we probably just call this one. Yeah, so just to define our options. So far there are nothing happened yet because we just define the architectures of our models. Okay, so the next step is the most exciting part. So now we can train our models. So you can use the train network and using our training data as input, and also the layers and options to use the input variables. So once we execute this line, you should be able to see the training windows pop up in your MATLAB. So depending on your computers, so it may show up in a variable speed. So for example, the computer the desktop I use to record this course is not very fast, but also not very slow. So it's just media core computers. But you can see that it is running the training very fast for different epochs. Okay, so the results are here. So you can see that this model achieved a validation accuracy of 99.76%, which is very high. And for this training progress, you can see that the top line show you the accuracy of the training. And you can see that here, there's a legend here. So the blue line here show the training progress, the accuracy of the training progress. And the light blue show the actual training results. So the dark blue show the smooth training line of these training results. But the most important is that you need to see this dashed black line, which is the accuracy of the validation result. So here you can see that the training and validation accuracy is roughly the same, which means that the model actually works very well in the validation data sets. However, if you train a model but you see a very high accuracy in the training data, but a very low accuracy in the validation data sets, then that is the problem of overfitting. Means that you have a high accuracy in the training data is overfit of your model, but that model doesn't work in the validation data. So sometimes you will see that once you finish your model, you will see the average validation accuracy here, but very high accuracy in the training model. But in this case, okay, this is very simple handwritten data set, and actually the model works very well, and the accuracy is very high. And also in the bottom figure, it show you the change in the loss across the training progress. So ideally, we want the loss to be as low as possible. But you can imagine that even you just train for more times, the result should be roughly the similar. So we can stop here for now, and this model works very well. Okay, so that is conclude this model, but finally we want to just calculate accuracy in using our codes. So just paste these lines, and you can see that the way we calculate accuracy is that the first thing we need to output the prediction of the class using the classify functions. Then we need to compare these predict values and actual values, and to find out the number of the correction of predictions, and divide by the total cases in the validation data. So I think I will leave it to you that you can try to plot a confusion matrix from these data. So I will leave that to you, but for now, the accuracy here, we achieved a 99.76. You might be wondering that why that number is different from the MATLAB documentation. In this documentation, the number is 99.88% accuracy. So the reason is very simple, because each training involves of the randomization of the data, and also the randomization in the training parameters. So that's why each training will result in a different, slightly different numbers. But if your model is a right model, then you should be able to obtain the similar numbers for each round. So don't worry about that your number is different from this one or the show you here. You should have a different number in your computers. But overall, you already learned how to build a very simple convolutional neural network. Okay, so this will conclude this week's course, and so I hope you understand the basic of the neural network, and then we'll move on to the real clinical data in the next few weeks. Okay, thank you very much. Bye-bye.